Now, for the last example that we'll do in this section, I typically assign this as an exercise to be attempted in class, and I usually give students, well, anywhere between 5 and 10 minutes, depending on how much is available, to try this problem on their own before I work through it with everyone together as a group. So we can't do it quite like that since we're not face-to-face this term, but we can do the next best thing, which is, how about you pause the video, try this problem on your own, and give yourself a chance to try it. If you get stuck, no problem. Just continue the video and we'll work through it together. And if you do figure it out, great. You can watch the video again after. You could watch the video afterwards just to confirm that you're on the right track and that you approached it correctly and that you got a valid solution. Okay, so I'll assume that you've taken the time to do that now, and now we're going to work through it together. So what we're asked to do is find two real numbers, whose difference is 100. So if you subtract the smaller one from the larger one, you get 100, really, what that means, right? And then whose product is a minimum. So that's what we're looking for. So, well, we'll start by making up labels for whatever we can. We're not going to draw a diagram here, right, because we're just talking about two numbers. I mean, what are you going to do, draw the numbers? You don't even know what numbers they are. So it's not really necessarily going to be helpful to draw a diagram, but what we can do is make up labels for everything in question. So let's make up labels for these numbers. How about x and y? Right, that's a pretty natural choice to represent the two unknown numbers. But we want to be specific here. Let's say that x is the lesser number and that y is the greater number. Right? It's going to be helpful to actually specify which one's larger and which one's smaller, so that when we go to actually unwind what it means for the difference to be 100, we know which one's being subtracted from which. Right? It just turns out you can actually make this problem a lot more awkward if you don't specify which of the two numbers is greater and which one is the lesser of the two numbers. Okay, so that's why I'm going to be specific there. And we want also the product to be minimized. And let me just remind you about the number line here. If you got the number line, minimized in this context means moved as far in this direction as you possibly can. So for example, if there's two, I mean, there's not going to be only two products that you can achieve, right? There's lots of different possibilities to take, but if you consider just two products, for example, say you computed the product of x and y, and in one case and you get -10. And then you do it again in another case and you get +1. Well, then -10 is the minimum in that case because it's further to the left on the number line. But now in our case, we want to make it as far as possible to the left on the number line, but subject to the constraint that their difference is 100. So subject to the requirement that if you subtract the smaller number x from the larger number y, you end up getting 100. So for that reason, we can do things like this. We can say, let's say P is the product, so the product of x and y, which we can write as xy, so that's the product. And the difference, well, that's going to be y minus x. So again, notice that I by specifying which one is the lesser of the two numbers and which one's the greater of the two numbers, I know that I can write the difference as y minus x. Because if I subtracted them in the wrong order, if I subtract the larger number from the smaller number, I'm going to get a negative difference, which cannot possibly be equal to +100. So it's important that I subtract the smaller number from the larger number. So that's why it's worth taking the time to be specific at the beginning. Okay, so what's our problem? We want to minimize the product. So we want to minimize P, which is equal to x times y. And then our constraint, subject to y minus x is equal to 100. Okay, so that's the first half of the battle, is to just identify what's being asked and express it as an optimization problem, because then once you get to this point, the rest is just systematic, right? You want to use this relationship, this constraint, to turn your function into a function of one variable. So, well, if I take the constraint and I solve it for y, I get y is equal to x plus 100, right? If I add x to both sides of that equation, so that means y is equal to x plus 100. So I can replace y in this product with x plus 100. So if I do that, I'll get P is equal to x times x plus 100, and that is our objective function written as a function of a single variable. So let's go ahead and do what we need to do. First of all, let's expand this out, and we're going to get x squared plus 100x. So we're going to want to find our critical numbers, look for a local minimum, because we want to minimize the product. That's what's asked for in the question. So let's, I'll start that over here. So we got all the space over here. There's no sense in wasting it. So p prime, if I differentiate p term by term, I'm going to get 2x plus 100. Okay, great. Let's look for critical numbers. P prime is going to equal 0 when x is equal to what? Well, how are you going to make this equal to 0? You need to make 2x equal to negative 100. So how is 2x going to become negative 100 if x itself is negative 50? Okay, so that's our critical number. When is p prime undefined? Never. Right, because it's a polynomial. And if you, after a while, once you get these problems down pat, and you can starts to become second nature. When you look at the derivative, if you know the derivative is a polynomial, it's never undefined. You don't have to explicitly write out your search for type 2 critical numbers every single time, but it is a good habit, right? I mentioned that early on in chapter 4. It's a good habit to do that. So it's better to write this out and have it turn out to not be necessary than to accidentally forget to check for type 2 critical numbers and then have it turn out that that was the one you needed. So I would recommend writing this out, but if you choose to omit this second step, that's okay too. Okay, so that's our critical number is x equals negative 50. Let me remind you of what would be a bad choice at this point. A bad choice would be to say, okay, x is negative 50. We can figure out y, right? Take negative 50, plug it in for x. We'll get negative 50 plus 100, and that's positive 50. Right, so that means y would be positive 50. We've got x is negative 50 and y is positive 50. That's my answer. Right? What's to stop me from just concluding that that's the answer? Right there. That would be the two numbers. Right? The difference is 100. Right? If I go positive 50 minus negative 50, based on I didn't write it down because I don't want to go this way yet. But based on what I wrote down or said out loud, we would get y is equal to positive 50. And if I subtract negative 50 from that, I'm going to certainly get 100. So that seems to work. But the problem is that I don't know for sure that this negative 50 is where the local minimum occurs. All I know is that it's a critical number of the product function p. So how do we check if it's a minimum? Well, we got two options. We can use the first derivative table and use the first derivative test, or we can use the second derivative test and calculate the second derivative, p double prime, right? You got two options available now. Because the numbers are fairly simple in this case, let's do the first derivative test. Let's set up our first derivative table for the function p. So the first derivative table is going to look like this. We've got one row for p prime and one row for p. Right, so we've got our critical number of negative 50. We can choose sample points. How about negative 51? That's a little bit to the left of negative 50 on the number line, and then negative 49. So those are the numbers I'll use. So if we plug negative 51 into p prime, so plug it in for x, well, 2 times negative 51, or how about this? It's probably easier to think about if I do this. Let's factor the 2 out, and we get 2 times x plus 50. Now you can see it a little more easily. If I take negative 51 and plug it in for x, well, negative 51 plus 50, that's negative 1. So you have 2 times negative 1, which is negative. So p is decreasing for values of x that are less than negative 50. And if I plug in negative 49, negative 49 plus 50, that's going to be positive 1. So you have 2 times positive 1, which is positive. So the function's increasing. Okay, so that now we know. Now we know that there is a local minimum that is achieved when x is equal to negative 50. So that now you can actually do the conclusion that I mentioned earlier. But let's go through it more carefully from scratch. So we do know that the product is minimized. So we can say, therefore, p has a local minimum when x is equal to negative 50. Okay, so, well, then what are the two numbers, right? Because that's what we were asked to do. We were asked to find the two numbers whose difference is 100 and whose product is a minimum. So, well, we know that the second number, y, is equal to x plus 100. So if we found what x is, we can figure out what y is. Right? So we know that x is equal to negative 50, so when x is equal to negative 50, y is going to be equal to, well, negative 50 plus 100. Right? Just using this relationship up here. Just add 100. Okay, so that's going to give us positive 50. So that means those are our two numbers. X is negative 50, the lesser of the two numbers. Remember, x was the lesser number and y was the greater number. And that's certainly consistent here, right? X is the lesser number. That's further to the left in the number line than positive 50 is. So, and if you multiply them, you're going to get a product of, well, if you actually multiply these numbers, what would the product be? So the minimum product, I'll say the minimal product is given by, well, x, which is negative 50, and y, which is positive 50. If you multiply those numbers, you're going to get negative 2,500. Right? This is just a side note. We weren't explicitly asked for this in the question, but I just want to spend a moment mentioning it because I think it's useful to think about this. Ask yourself, why does that make sense? We were asked to find a minimum product, and that seems like a huge number, 2,500, and it is a large number in magnitude. But because it's a negative number, it's actually very, very far to the left on the number line. So remember, that's, if you were to actually plot negative 2,500, it'd be very far in this direction. So that's what we mean by the product being a minimum, right? It's the least number you could possibly get, in the sense that it's the furthest to the left on the number line that you could ever possibly achieve, while still preserving the fact that their difference is equal to 100. And of course, there certainly is, right? If we go 50 minus negative 50, we get positive 100. So they do satisfy that constraint. So anyways, I'm babbling here, but the point is that just because the product seems like a large number in magnitude, it is, that doesn't mean that we haven't minimized it, because of the fact that it's negative, right? That negative sign comes to the rescue here. So in any event, let's finish this off. The two numbers are negative 50 and 50, right? So that's going to be our final answer here. Okay, and that concludes that example, and that concludes the section.